Humanity builds its systems on the assumption of infinite loops. We model our economies on the promise of perpetual growth. We engineer machines we expect to run forever, and we treat digital storage as an endless, frictionless void. But physical reality prohibits these endless cycles. Every time you move an object, burn a fuel, or flip a switch, the universe extracts an inescapable toll. Entropy is this universal toll. You have likely heard it described in high school as a measure of disorder, often compared to a messy room or a shuffled deck of cards. You need to discard that metaphor completely. This diagram shows how thermodynamics defines entropy. It is not subjective messiness, but the objective spreading of energy. A concentrated, low-entropy state will naturally dissipate outward, settling into a vast, evenly spread grid of particles, because that state is statistically highly probable. This makes entropy a universal transaction cost. You cannot perform work, process a line of code, or even take a breath without paying a physical price directly to the environment. Engineers during the Industrial Revolution were the first to identify this cost. They realized no matter how tightly they sealed the valves on iron mechanics, like this Marshall steam engine, their machines consistently lost power. The physicist Rudolf Clausius formalized this observation. He determined that no engine can be perfectly efficient. A specific fraction of the heat used to drive the pistons must be rejected into the surrounding environment as unrecoverable energy. By the late 19th century, Ludwig Boltzmann shifted the scientific focus to the microscopic behavior of atoms. Looking at this animated scatterplot, we can see Boltzmann's breakthrough. The tax is a mathematical probability. A highly organized clump of particles rapidly randomizes into unpredictable microstates, because there are vastly more ways to spread out than cluster together. The laws of physics technically allow those scattered particles to spontaneously gather back into a neat, low-entropy corner. However, the sheer volume of possible arrangements makes the math virtually impossible to observe in reality. What began as an engineering problem in Victorian boiler rooms and factories became an absolute rule of statistical probability, proving that the flow of energy is strictly a one-way street. It is tempting to think our modern digital world escapes the physical constraints of steam engines. After all, a modern server farm processes abstract data rather than physical coal. In 1948, the mathematician Claude Shannon proved that digital information and thermodynamic entropy share the exact same mathematical structure for measuring uncertainty. A decade later, the physicist Rolf Landauer took this a step further, proving that logical information is a physical entity. Look at this digital bit being erased. Landauer proved resetting it to a blank state requires dumping thermal energy into the environment. As computation scales up, these pulses aggregate. The math gives data physical weight, proving forgetting generates a quantifiable heat cloud. Every time a data center clears a cache or deletes an email, it is irreversibly paying the universe's thermal tax, converting abstract logic into measurable physical heat. This creates a paradox. If the universe mandates energy dispersal, biological life should quickly decay into scattered atoms. Erwin Schrödinger solved this by defining living things as open systems. Organisms maintain their complex internal architecture, like the organized instructions encoded in DNA, by constantly feeding on structured energy and exporting massive amounts of heat and waste outward. Human civilization operates on the exact same thermodynamic principle. Ecological economists view our entire global society as a single massive organism. The economist Nicholas Georgescu-Roegen argued that our global economy survives by extracting highly ordered, low-entropy resources from the Earth, chewing them up to perform work, and irreversibly degrading them into high-entropy waste. Because the Earth's stock of these structured materials is strictly finite, the universe's entropic tax puts an absolute physical limit on resource extraction and perpetual economic expansion. When we scale this up to the cosmos, entropy provides the singular physical distinction between the past and the future. It is the physics engine driving the arrow of time. The mathematical progression of this one-way street leads to an era known as the heat death, or the dark era, where the entire cosmos reaches perfect homogeneous thermal equilibrium. As shown in this simulation, energy will eventually be entirely evenly distributed. With the temperature gradient completely flattened, particles will drift in near blackness, unable to perform the work required to ignite a star, power a cell, or process a single thought. This universal tax is the cost of transformation itself. Every star that ignites and every cell that replicates is a byproduct of energy rushing toward that final, scattered equilibrium. We inhabit the brief, turbulent window where the universe is actively spending